Hello everyone, I am Prashun Dhang, currently a postdoc at Tsinghua University, and I am going to talk about the generation of large-scale magnetic field in a radiatively inefficient accretion flow. We also study the transport of the field in the turbulent RIAF, and the work has been done in collaboration with my present and past collaborators. So here is the talk in a nutshell. We study the generation of large-scale field in a weakly magnetized RIAF where the angular momentum transport is mediated by the magnetic magnetorotational instability or MRI. We also study the transport of the externally imposed magnetic flux in the already turbulent RIAF. And we use MHD and GRMHD simulations to study this stuff. And here are the key results of our work. We found that Dynamo is inefficient in producing sufficiently strong large-scale magnetic field, which can generate a strongly magnetized accretion flow. We also found that not all the flux which are injected at the larger radii can reach the black hole, but a certain fraction of it can reach the black hole, overcoming different dissipative effects. So the first question would be why we are interested in studying the generation and transport of large-scale magnetic field. From the observations and different theories, we know that the jets in the accreting system are intertwined with the presence of a RIAF and large-scale magnetic flux close to the black hole. For example, in black hole binaries, jets are present in the hard state, and it is thought that in the hard state, a hot RIAF does exist close to the black hole. Also, the recent polarized image of M87 indicates there is a strong poloidal flux exists close to the black hole. Also, different numerical simulations so far have shown the necessity of presence of strong poloidal flux close to the black hole. So all this observations and theory and numerical simulations predicts indicates basically the necessary ingredient of producing jets in the accreting systems are hot drive close to the black hole and large scale magnetic flux. And these are essentially realized in numerical simulations in a model of accretion flow called magnetically arrested disk or MAD, where the black hole is surrounded by a hot, thick accretion flow and threaded by a strong, large-scale poloidal flux. Now, there in a broadly speaking, the radiatively inefficient accretion flows or RIAFs can have two different kinds of magnetic state. One is MAD, we already talked about. These are highly magnetized, and this uh, magnetic state are realized in numerical simulations by initializing the simulations with a large scale, strong magnetic field. It can be either poloidal or toroidal. And this large scale magnetic field are eventually dragged in later time and create the MADs. However, there is another flavor of RIAF, which is weakly magnetized, called standard and normal evolution of SANE. And the simulations, these are realized in simulations by initializing the simulations with a weak magnetic field loops of different polarity. Now, we are essentially interested in how the dynamo action or transport of magnetic flux in the same models can reach the MAD state or not. So first question would be, what is the source of large scale magnetic field in the first place? So one guess would be that the magnetic field itself is generated in the accretion disk by some MRI driven dynamo, because it is almost current consensus that uh, angular momentum transport and turbulence in the weakly magnetized accretion flow is mediated by the MRI or magnetorotational instability. So MRI driven dynamo can be a first case, and the time evolution of the large scale magnetic field can be governed by this main field evolution equations. Now, if we expand the equations, it can be easily identified that whether the generation of large scale magnetic field is mostly dominated by the shear the generation of poloidal field is linked to the term called mean or mean EMF, which arises because of the correlation of the fluctuating velocity and magnetic fields. Now, this mean EMF can be correlated with the large-scale magnetic field, and it's in by using some closure called mean field closure. Now, so essentially, in the dynamo, in the mean field dynamo, the generation of poloidal field is is governed by the alpha effect, and the generation of toroidal field is mainly governed by the omega effect or shear. So how this cycle basically goes on and and maintains the balance between toroidal and poloidal field. And the question would be that, can dynamo in a same lead to a mad state? So we use the global MHD simulations using the Pluto code to study the dynamo in a weakly magnetized RIAF. We also characterize the dynamo coefficients in our previous work. But the first thing generally people would do to study the dynamo is to look at the butterfly diagram. Butterfly diagram is nothing but the variation of azimuthally averaged toroidal field with time and latitude at a fixed radius. So here is the butterfly diagram from our simulations, and we found the typical signature of a geometrically hot thick RIAF, that the dynamo cycle is intermittent, and this irregularity in the dynamo cycle is due to the slightly subcapillary nature of the angular velocity. And if we compare it with the so-called in the with the butterfly diagram in the thin disk, which is kind of very regular and flips, the sign flips around in 10 orbital time, and we can see it from this. We can compare it with the thick disk, thin versus thick disk. We also characterize the type of dynamo in the MRI driven dynamo. To characterize it, we look at the meridional variation of three different control parameters, which are dimensionless numbers called alpha, R alpha, R alpha phi phi, and R omega, where the former two describes the importance of alpha effect, R omega describes the importance of omega effect. And if we look at the variation of R alpha, R, this control parameters with latitude, we found that R omega surfaces the all other R alphas at all latitudes. And this indicates that generation of toroidal field is mainly governed by the omega effect or shear, while the generation of poloidal field out of the toroidal field governs by the alpha effect. So the dynamo is essentially alpha omega dynamo. We also found that the alpha effect is weak, and they do not really produce the strong enough poloidal field which is required to produce MAT. So our results are essentially in line with the previous results, which found that if we start the simulations with weak magnetic field loops, and they reach the same and they never become mad, with which contains the strong poloidal flux close to the black hole. So essentially, it appears that the initial uh, magnetic field configuration matters. We need strong large scale fields, either it be toroidal or poloidal, in order to reach the mat. But what what can be other sources of magnetic flux in the accretion disk? So RIAF actually potentially it can have an external source. For example, in X-ray binaries, the companion star can contribute, or in low luminous agents, the contributor can be the accreting ambient medium. And the natural configuration uh, is most likely to be in the form of closed loops of the magnetic fields. And to study the magnetic flux transport or to study the external the flux transport of this external flux, as a first approximation, we use the magnetic field loops, and we inject these loops uh, in the already turbulent weakly magnetized RIAF, namely SANE, and we follow its evolution. So we used GRMHD code Ethana++ to study this, but we also know that an effective resolution of sufficient resolution is required to attain the convergence. Following the past works, we use 42 grid points per scale height in the vertical direction, mm, and we use static mesh refinement to achieve these resolutions. Also, we want to maintain the simulations, RIAF simulations, to be in the same regime. So we initialize the simulation with small poloidal field loops of alternate polarity, and we expect that in the quasi-stationary state, the simulation will forget the effect of initial condition, and the magnetic field generated at late times will be mostly due to the underlying dynamo action. So here, let's say, look at the evolution of the accreting of our simulations. So right hand panel shows the this variation of the azimuthally averaged toroidal magnetic field, while the left hand panel shows the variation of the azimuthally averaged radial magnetic field, and streamlines shows the basically the poloidal field lines. So as you can see, after this initial transient phase where there is a strong enough strong poloidal flux along the poles, it just gets weakens over time, and in the quasi-stationary phase we see the a highly turbulent midplane and a weakly magnetized polar regions. So in the quasi-stationary state, we essentially found a hot RIAF with the thickness of h over r of 0.25, and the system with an inflow equilibrium radius 60 rg. Essentially, the inflow equilibrium radius is the radius within which the system is in a quasi-stationary state, and this can be realized by looking at the radial profiles of the mass accretion rate at different times. Here, the blue line shows the radial profile of mass accretion rate at the very late time, and we see that the m dot suddenly goes down at around radius 60, and this is the radius within which the system is in a quasi-stationary state. We also looked at the magnetic state of our simulations. To quantify it, we looked at an empirical uh, quantity called MAD parameter, or 5VH, and it states that if the 5VH is above a critical value, the system is in a MAD state. And we looked at the time variation of 5VH, and we found that the value of 5VH in our simulation is well below the critical value. So we confirm that our simulations always remains in the same regime. And we want to look at the flux transport of this in this weakly magnetized RIAF or SANE. So we use magnetic field loops of different strength quantified by the plasma beta, of different vertical size, of different radial size. We also look at the uh, effect of point of injection of these loops, as shown in the last two panels, where we have shown the offset that the location of this off-centered loops. So first we will describe the time evolution of the of our fiducial run for the injected loops. The fiducial run has a plasma beta of 1500, and the loop is located between 60 and 90 Rg, which can be easily identified in the left hand left hand panel. So this movie is very similar to the previous movie. Right hand panel shows the azimuthally averaged toroidal field, left hand panel shows the azimuthally averaged radial field, and the streamlines depicts the streamlines as poloidal field lines. So as you can see that due to MRI, the loops are getting turbulent and they are slowly drifting towards the black hole, and it enhances the magnetic field strength close to the black hole. And if we compare it with the same run uh, at the same time, we can find that the the run with the injected flux are quite stronger than the original sen run. We also want to see a case where the loop is very strong with plasma beta 70, and this kind of betas are generally used to initialize the magnetic field loops in the MAD simulations. Here the loop is also located at the same location, and if we look at the time variation in this movie, we can easily see that unlike the previous case where the magnetic fields are getting turbulent and slowly diffused to the black hole, here I'm running it again. The the magnetic fields are just plunges in to the black hole very quickly, and it enhances the magnetic field strength close to the black hole quite strongly. But a better question would be that how much fraction of this injected magnetic flux are essentially reaching the black hole. To quantify it, I look at the ratio of the flux threading the black hole and the flux injected at the outer radii. So the top left panel shows the time variation of this ratio or fraction for different plasma beta, and as you can see that almost 15 to 40% of the flux are essentially reaching the black hole, while for most of the cases the fraction is around 15 to 20%. It is worth noting that for the two cases, for beta equals to 1500 and 700, a larger fraction of the magnetic flux are essentially reaching the black hole. So apparently it looks like that flux transport is most efficient for an intermediate range of beta. But however, to put this comment on a firmer footing, we need to explore it as slightly more. We also look at the efficiency of flux transport with the vertical size of the injected loop. So in the top right panel, we compare the fraction uh, of a taller loop with the fiducial size for beta equals to 1500, and we found that the that the vertical size doesn't really affect too much in the flux transport efficiency. Same happens with the radial size, mm, as shown in the bottom left panel. An interesting thing happens for the off-centered loops. Off-centered loops are turning out to be less efficient, very inefficient uh, in order for the flux to be transported close to the black hole. The reason is the following: the center of the off-centered loop resides in the northern hemisphere in our simulation. So, and due to shear, both positive and negative polarity toroidal fields are generated in the northern hemisphere itself. And it is to be noted that toroidal fields are the dominant configuration in the accretion flow because of the presence of a strong shear. So due to the presence of these opposing polarity fields in the same hemisphere, the probability of reconnection uh, enhances, and it basically destroys the magnetic fields. So, uh, in our study, our study actually, what could be the physical significance of our study of this field transport? Uh, if so, we found that not all the fluxes are are reaching the black hole, but a certain fraction of it. But we are in a very narrow parameter space. At a Our loops are mostly located between at 60 or 60 to 90 RG, 60 to 90 gravitational radius. Now, if these results can be extrapolated to a larger radii, this will help us to give some idea in which ambient medium the accreting flow will attain a mad-like state and will be a good favorable can provide a favorable condition for the jets. However, to to understand it in a better fashion, we need to explore these ideas more before reaching any concrete conclusion. So here is the summary of our result. We found that in a weakly magnetized RIAF, where the turbulence is governed by the magnetotensile instability or RIAF, the dynamo is unable to generate strong enough poloidal flux, which can produce a magnetically arrested disk, which is the favorable for the jet production. We also look at the transport of externally imposed magnetic flux, and we found that not all the flux can essentially reach the black hole, but a fraction of it can essentially does reach the black hole. We also find that the size of the magnetic loop field loops doesn't really affect the transport efficiency, at least in our parameter space regime. And off-centered loops are found to be uh, very inefficient for the flux transport. Also, we found that flux transport is most efficient for a range of plasma beta around 1000 in our chosen parameter space. So here I end the talk, and thanks for your attention.